me this opportunity to talk about another event that's happening this weekend that is related to topics that Tony has contributed to and has continued interest in. So we felt that it was appropriate for me to present what we're doing tomorrow for this public quantum network launch event. So we're going to celebrate the launch of the first publicly accessible quantum network in the nation, and we think it in the world. And our tagline is where everyone can play with quantum particles. Come explore with us. So I know that the workshop continues tomorrow. This is happening from 1 to 4 p.m. But you're welcome to, if you're interested, we can show you our labs. And if you have extra time on Sunday, you can always go to the library to see what we're going to install tomorrow there. All right, so let me tell you what this is all about. Yes, it will be streamed as well. And so we're sharing that link with the organizers, and perhaps they could even show that on the screen during lunchtime as we set up that event. So in addition to presenting and demonstrating a quantum network, we're also going to be explaining to the public, various aspects of what quantum networks are, including philosophical implications. We'll also be having activities for kids. So this is really for everyone. Right, so what is it? Well, here in Urbana-Champaign, we have an unusual situation where we have a fiber optic network that is accessible to the university without having to go through private companies like AT&T and Verizon. And it turns out this fiber optic network is all optical, and it uses state-of-the-art fiber that is suitable for building a quantum network that uses single photons. And so this network is called UC2B. And we're making use of this to actually build quantum network nodes in public institutions. And so tomorrow is the first node that we're installing at the Urbana Free Library. So just to give some historical buildup to how we got here, in the 1930s, of course, Einstein and colleagues had difficulty accepting the implications of quantum mechanics. In 1964, John Bell came up with a way to test for entanglement. And since the 1970s to the present, experiments have been done and improved to show definitively that indeed entanglement exists. It's a property of this universe, and that quantum mechanics is correct. On that pathway, Tony had a few contributions, and I just want to highlight those. This is quantum mechanics versus macroscopic realism. Is the flux there when nobody looks? And he made the point that perhaps the one that is most applicable to what we're doing tomorrow, which is the CH-SH inequality, is this paper, Non-Local Hidden Variable Theories and Quantum Mechanics, an Incompatibility Theorem. And there's an interesting story that he shared. The reason why that little notch is actually a huge bar is because he actually wrote this paper in the 1970s when he didn't have access to journal articles while he was in Ghana. And he found this topic perhaps didn't have much existing literature on the topic, so he thought it would be a safe one to work on. But he actually didn't publish it until 2003 when he was encouraged by colleagues to do so. Perhaps he was busy doing other things, I'm not sure. In 2022, just last year, the Nobel Prize also went to the people who did the first Bell test experiments. And now this year, we can do something where we're taking this technology to the public. And I just want to highlight the fact that this is really reflected in Tony's spirit of reaching out to the public. This is a photo of him at the Urbana Farmers Market talking with a little kid about quantum physics, perhaps. And so in that spirit, we're reaching out and sharing this technology with the public, not only because we want to do outreach, but also we believe that getting their involvement is important at these early stage of this technology so that it really works for everyone. Okay, so what is this network link that we've created? In Loomis Laboratory on the 3rd floor, my lab and Paul Kwiat's lab has a source of entangled photon pairs. And those are sent through the fiber optic links over to the Urbana Free Library, which is only about 2 kilometers away. But we actually end up going through something like 12 kilometers of fiber just because of the way it's routed. And here's a video of what happens. So in my lab at Loomis, we have an optical setup, and that's a Sagnac loop that generates pairs of entangled photons. And one photon from each pair is sent over to the Urbana Free Library through optical fiber. Whee! So we get to enjoy the path of the photon as it goes underground through the fiber optic network, under traffic, which causes problems for us. Actually, we can see the polarization change on high traffic days, moments, and then it goes into the library where it flies out into air, and the public can then turn a wave plate and choose the measurement setting in which to measure the polarization of the photon. They just choose the setting. The measurement itself is done back at our lab. So once they've made that choice, the photon then returns back into the optical fiber through the ground, past all those cars. I mean, it does go much faster than this in real life, fortunately. And then ends up back in our lab at Loomis, where we then do these measurements to see if indeed the two photons are entangled. And the test we're doing is the CH-SH inequality. So let me move on here. Right, and so here's a little bit more detail. At our lab, we have the Sagnac loop with, for those who are familiar with these kinds of experiments, we have PPKTP crystal. That's our nonlinear crystal where we generate photon pairs, and then we get the state HV plus VH out. Of course, when we present this to the public, we call it HH plus VV, just to simplify things. So in case you hear us say that, that's what we're trying to do there. And then at the library, this is what we're leaving behind for people to interact with from tomorrow on. So we have on the left side, this is the interactive portion. This is where they sit down and can turn a wheel. And that wheel is the wave plate where they choose the setting for the polarization measurement. And then hidden from them is on the right side, something that's in the network closet. And that literally, you can see optical fibers. That's where the photon comes out, goes through the wave plate that is motor controlled as they change the wave plate over at the interactive setup so that they can directly influence what measurements are made at the library. The photons are then sent back to our lab to be detected. So why are we doing this? Well, one, for foremost, it's this public engagement aspect, giving them the chance to participate in quantum technologies, to give us feedback on, positives and negatives, perhaps even ethical issues that they see with quantum technologies, and to bring them in and build a workforce around quantum technologies, especially amongst underserved communities. So including quantum curricula in 8th grade through community college classes. But of course, this is also cutting edge research. So actually building this network requires us to solve problems that haven't been solved yet. So once we have a network that has many nodes, so we plan to expand this out to more and more places, we can do state-of-the-art quantum protocols and fundamental tests at scale with more than 2 nodes, even dozens of nodes. As well as bringing in our industry partners for innovating technology. So this is just the first step. We have this large map. We've just got 1 node. Our next node is going to go over in Champaign at a recreation center that's there. And we've also got links up to Kankakee, which is kind of halfway to Chicago. There's a community college we're going to link up there. And we just got DOE funding to install a node right outside Fermilab in Batavia. So this will expand hopefully fairly quickly. And eventually we'll be actually doing real quantum networking over these distances. It's a large team behind it, so I just want to highlight all the graduate students and undergraduate students, faculty, staff, the people at the Urbana Free Library, and communications team that are all behind this. And and I welcome your questions. Thank you. So tomorrow we're doing the CH-SH inequality demonstration, and that's what people can do right now. And then we're going to try to promise QKD by, like, let's say Valentine's Day, so they can send Valentines to people using QKD. That's kind of the goal. Yeah. Yes, so the measurement result pops up on the screen. We have a computer screen right there at the setup, as well as is posted automatically on our website. And then we also plot the results for the angular difference between the two settings to show them that there's an optimal setting. Yes.
Yeah, the speed of light down to what you showed us, either delay twice.
That's right. Yeah.
What is the loss of this stuff?
So it's 10 dB, so it's about 10% of the photons make it all the way back to us that are sent over. Yeah. Yeah, it's not bad.
Gina was
Okay.
good.
Thank you.